Okay, great. Thank you very much. And yeah, it's a real pleasure to be here. And thank you very much for the invitation. So yeah, in the spirit similar to the previous speaker, I've kind of looked back over my career of 20 years to date and tried to pick out a few different topics. So rather than focus on one thing and go very deeply, I've tried to take a few different examples and give you a flavor of the different things that can happen. So let's get started with that. So there are many, many people involved, but in particular, these 6 people have really been very generous supervisors in some cases, or bosses, but also collaborators. And so, as you can see, there's a variety of places around the world. So in the UK, in the Netherlands, Japan, US, and I've been in Bristol now for about 10 years, working with Ross and Jerry in particular. So before we go on to the 3 topics, I just want to briefly try to motivate thin films. This is a nice picture taken from this report at the top of the script, at the top of the page. Oh, let me see if I can use laser pointer. There we go. Yeah. Okay. So this is actually a paper discussing heavy fermion thin films, of which there are very few, and I'm kind of interested in heavy fermion thin films, and that will become clear later why. But why are thin films interesting? Well, most of our electronics are based on thin film. They're really important. If you want to get some piece of condensed matter physics into the real world, you probably need to make it as a thin film. But you can do lots of really interesting physics as well. You can confine, you can electrostatically gate. I won't talk through all of these here. There are many examples as to why thin films are really interesting as well as being useful. Your ability to combine different materials together to get new things. So that's kind of a bit of thin film propaganda in some sense, rather than bulk. But let me dive straight in and give you an example. So this is work done with Howard Wang and Yasuki Ikita over many years, talking about oxide heterostructures. And we heard in the previous speaker talking a little bit about transition metal oxides. So this is very related work. Okay, so the idea is you have some transition metal oxides. These are very commonly perovskite structures. So this is the prototypical perovskite unit cell. It kind of looks like a Lego block because there are many materials that share similar crystal structures and can be stacked on top of one another. So that's the kind of idea. You can build new materials. It's a materials by design concept. And in the simplest case, if you take 2 materials, so here A is some element, B is some element, and O is oxygen. All we've done here is switch the B element, so B to B primed. And if you stack these materials together, the interface is a brand new material with this chemical composition. And this may not exist in nature, and it can give you new physics. So that's the idea. Can you do it? There are many ways to do it, different thin film growth techniques. I'm not going to go into them. This particular image here is a transmission electron microscope image of a combination of strontium titanate, this material here. These 5 dots here represent a row of probably 100 atoms into the page, but this is atomically resolved imaging. And then this brighter row here is one unit cell, one crystal unit cell of lanthanum titanate. So again, you're just changing one chemical element, lanthanum, to strontium. So you can build up these artificial materials in a layer by layer way. And this was done by Howard and his collaborator Akira Otomo 20 years ago now. So what he discovered a few years later is actually if you take these 2 materials, it's this material material strontium titanate again, which is the most important character. You stack lanthanum aluminate on top of this material. So these are two materials with very similar crystal structures, as same crystal structure basically, and very similar lattice parameters. So these Lego blocks are nearly the same size; they stack together. And nominally, they're both insulators as well. Lanthanum aluminate is a real rock. You can't make it conducting very easily. Strontium titanate, actually, if you dope it, like silicon, you dope that to become a conductor, you can dope strontium titanate to become a semiconductor and actually ultimately a superconductor as well. But these 2 materials, when they made them, were insulators. And they put them together, and one of the interfaces, there are actually 2 choices, but one interface was highly conducting. So this is resistance versus temperature. It basically looked like a metal. If they made half a unit cell, so 1 atomic layer change to the structure, it was insulating. So there was a massive difference between the electrical properties of these two interfaces based on a few angstroms, fractions of a nanometer change in the crystal structure. So this was, again, 20 years ago, ignited a huge field of research and interest. There was about a decade-long debate about why this was happening. And I'm not going to get into that. It was very interesting. I'm kind of half physicist, half material scientist. There's a really interesting discussion about competing ideas. Actually, many of them are not independent of one another. For young researchers, these materials are complicated, and I'll come back to that later. Basically, it's very hard in cutting-edge research to come up with this kind of golden bullet that solves everything. Everybody was making their samples in a slightly different way, and it was very difficult to come to some clear conclusion, partly because of us and our ability to reproduce each other's work, but also because these materials are complicated. So I think that's an important lesson to remember, that the real world sometimes can be messy. But stepping back from the materials, in terms of the physics, there was some really interesting physics. This interface, which was metallic, if you cooled it down colder, it became a superconductor. And it turned out to be a two-dimensional superconductor. So here are just some resistance versus temperature plots in various magnetic fields. And this was work done by Jean-Marc Toscani's group in Geneva. They basically showed that in order to destroy the superconductivity, you need some magnetic field, but the magnetic field required in the plane of the sample compared to, that's this one, Tesla level, compared to perpendicular to the layers, 300 millitesla, so much smaller, there's a big difference suggestive of a very thin layer of superconductor. Okay, so it's a two-dimensional superconductor, but it also showed quantum oscillations at higher magnetic fields. I won't go into the details of this. They're not incredibly convincing oscillations, but they're there and could be shown to be two-dimensional as well. And this actually was only probably the second time. We'd done some studies in a slightly related system a few years earlier, but this was only the second time where these two phenomena had been seen in the same material system. So that was already quite interesting, that we can have a two-dimensional material in two senses of two-dimensional superconductivity, and the Fermi surface was two-dimensional as well. And what was particularly interesting is that this is more like a semiconductor than a metal. So, in your phones and so on, we have transistors, we can field effect gate, and we can make superconducting transistor now, which is really interesting. And we can do it in two ways. So we've got actually what this strontium titanate crystal is a big lump. It's a substrate 0.5 millimeter thick. So we just buy this as a commercial material. So it's very thick, but it has a very large dielectric constant. So you only need to apply a few hundred volts, and you can field effect gate this interfacial superconductor. Or we have lanthanum aluminate, which is a few nanometers thick, so orders of magnitude thinner. Dielectric constant is smaller, so it's less easy to move charge. But because it's so thin, the capacitance is very large. So we only need actually a few volts to move carriers into the interface or away from the interface and to tune the superconductivity. So we showed actually from the top side, you can get virtually ideal transistor properties. This was actually at room temperature. So that was very easy to do. Looks textbook-like, fantastic. And again, the group in Geneva showed from the back side that you could remove electrons from the system. And now this is blue data to focus on. This is the superconducting transition temperature as a function of gate voltage. And you could basically pull out all of the electrons and switch off the superconductivity. And this was a really big deal, 16 years ago. Initially, they wanted to claim that this was a clean, carrier density driven transition into a quantum critical point at 0 Kelvin here. Actually, it turns out to be not so easy, because the mobility, the scattering in the system is changing consistently as you deplete the electrons away. So this wasn't quite so clear as they initially wanted. But still, it's a really beautiful example of tuning a material with a parameter which we don't always have access to. You can't do this with a metal, for example, because the carrier density is too high. So this is a kind of intermediate between traditional semiconductors. This is an example of zinc oxide, gallium arsenide, silicon, high mobility, low density semiconductors, which are typically not superconducting. That's one end of the spectrum. The other end of the spectrum are materials which are typically superconducting. They might have high electron density, but very low mobility. There's lots of scattering. And so we're somewhere in between here, and that transition is really interesting. Ultimately, we want to look at, actually related to the previous talk, how the quantum subbands impact superconductivity. That's a bit of a complicated story, and I won't have time to talk about that now. But what we were also interested in is, can we see the quantum Hall effect in this system, in this oxide system? And there are various ways to go towards that. And actually, again, it's a material science problem, trying to make systems cleaner. People were playing around with the composition of the structure, using other oxides, making new materials again. And they got close, not quite to the single subband quantum Hall effect yet, but we're getting in the right way. A final comment on this section. Since we're in London, I stole that logo. The problem with these materials is that they're very sensitive to just about everything, and particularly this very thin layer of oxide on the surface. So you have a few nanometers of some material, and then this conducting interface underneath it. So actually, if you do anything to the surface, you're probably also going to interact with the interface below. So we found actually that cleaning the system with water or acetone or ethanol, any polar solvent, actually field effect gated the system. So that's kind of tricky for an experimentalist who likes to keep their samples clean. You can also statically charge the surface and gate the layer below, which is really interesting. Jeremy Levy's group in Pittsburgh pioneered the ability to draw circuits on the crystal. So there was some really interesting physics, and this continues to, some of these references are quite old now. This continues to be a really interesting area. But again, as a comment on materials at the cutting edge, these things are complicated and sensitive to lots of different interactions and different ways you might think, oh, I'll just clean the sample, make it a bit nicer. Actually, you've fundamentally changed your sample. So this is quite an important thing to remember as an experimentalist. Okay, so changing gears, I'm now going to talk about something much more simple, in inverted commas, which is an elemental material, uranium. So this is work I've been doing in the last few years with Ross and Jerry in Bristol. So just as a quick advert, we can grow thin films of uranium and thorium in Bristol. So we have a facility called Farms. This is the cow logo that you may have spotted on my opening slide. It's a bit strange. Oh, yeah, don't blame me for that. So most people don't really like contaminating their vacuum systems. This is our vacuum system where we grow our samples. They don't really like contaminating it with radioactive material. But we've decided to do that. We're the only place in the UK that can currently do that, and one of only a few places in the world. So this is really interesting. We're interested in heavy fermions, for example, many of which are uranium-based. But for everybody else out there, what's interesting also is this chamber is a bit radioactive, but actually our samples are not. They're so thin, for most metrics, they're not radioactive. And so if you want some uranium samples, please have a word with us. It's often the case that you can accept them, even if your institution does not have a license for that. Okay, but let's talk about uranium. It's a heavy element, heaviest naturally occurring element. It's a superconductor, maybe. It's a bit controversial. So it's been known for about 70 years, but actually the superconducting transition jumps all over the place. And this one down here with 0 TC is the cleanest crystal. So the best crystal is not superconducting. So that's kind of interesting. It also shows charge density wave states. So it looks like a high temperature superconducting cuprate, but it's an element. Yeah? The CDW is quite complicated. There are various transitions, various Q vectors. I won't go into that. In thin films, we can actually boost that charge density wave transition up to about 100 Kelvin. So we're using strain to do that. I won't talk about that either. But uranium is generally interesting because of this. It's heavy element. We've just heard about spin orbit coupling. It will be multi-band. How does it interact with the CDW? Loads of really interesting questions that have never been answered in the literature. It's also interesting as a spintronic material. So one of my colleagues, Martin Gradhand in Bristol, predicted that it should have a very large, this is the spin Hall conductivity. So for things like the spin Hall effect, it should have a very large spin Hall conductivity. Again, because it's a large element, strong spin orbit, as we heard in the last talk. Actually, Martin did this for 3 different crystal structures: the alpha orthorhombic phase, the hexagonal close pack phase, and the gamma, which is BCC uranium phase. And actually the HCP phase, this orange curve here at the Fermi energy, showed the largest predicted spin Hall conductivity. So that was theoretical prediction. Slight problem is that on the structural phase diagram of uranium, despite it being a bit complicated and interesting, there's no hexagonal close packed phase. It doesn't exist in nature. So there's an orthorhombic phase, that's the one I just talked about, which is maybe a superconductor. There's a tetragonal beta phase, which is hideous, so let's not talk about that because it's very complicated. There's a gamma phase, a BCC phase, and then many years ago, 30 years ago, there was a prediction that actually the BCC phase would relax to the orthorhombic state via a hexagonal intermediary. And actually, there are a few examples in the literature where this HCP phase had been stabilized at the surface or in thin film form. And we wanted to go after this and understand the HCP uranium. So we had a really talented PhD student, Becky, and she discovered with a simple ball and stick model that if you take copper 111 surface, this is the close packed surface, she predicted that hexagonal close packed uranium would line up perfectly and be epitaxially matched to the copper 111 surface. So very small compressive strain. So the uranium should adapt to that and adopt this HCP structure. She also found a slightly related one with iridium. So iridium was also a templating material with a slightly tensile strain. Okay, so what we did was a very simple thing. Forget single crystals and high temperature growth and all fancy things like that. Actually, room temperature growth, the copper and iridium like to form in this 111 close packed surface. So we just did samples of copper and iridium, and then we grew uranium on top. And we could do that. So we stabilized this hexagonal close packed phase. This is an X-ray scan, so X-ray intensity versus angle, and a simple diffraction pattern. And this peak, let me focus on this peak. This is the hexagonal close packed peak. We saw clear evidence for it. But then within hours, days, weeks in some cases, that peak decayed and died away, and we lost the structure. But at the same time, we gained a peak, and this is the thermodynamically stable alpha orthorhombic peak. This is very weird. This doesn't usually happen. It was completely unexpected. I should say, actually, the previous work that Howell did on lanthanum aluminate strontium titanate, that was completely unexpected as well, completely serendipitous. So again, for young researchers in the audience, sometimes things jump out at you and are surprising. So these are really interesting usually. So this peak decayed over the matter of weeks, and we could follow that and try to understand how this was happening. So yeah, technically this is something called a topotactic phase transition, a structural transition where instead of ripping itself apart and falling into a powder, which often happens, it actually smoothly transformed into a different crystal. This was really interesting. The crystals that it transformed into was thickness dependent. So that was a bit weird. I won't go into the details there, but really we wanted to understand why this was happening from a fundamental point of view and how those atoms are moving smoothly, carefully, without ripping the crystal apart. So we had some very good collaborators in Paris who could do phonon theoretical calculations. So this is a phonon spectrum now, so phonon energy at various directions in the reciprocal lattice. And so these are two different types of sample, blue and red, depending on the lattice parameters of the crystal. And there are only a few examples. So here are two other publications where people had measured the lattice parameters of hexagonal close-packed uranium. And here are our new data. And so for people who are really experts in these kind of things, actually, these numbers vary hugely. So there's something funny about uranium. It's a very, very complicated material. It seems to be much more malleable. The crystal structure is much more adaptable than we expect. And this part down here, these negative energies, are instabilities, theoretically predicted instabilities. And you can see that the position of these instabilities in momentum space is varying depending on the lattice parameters, specifically the C/A ratio. That's a technical detail. But those positions vary with the lattice parameters that we have. And those lattice parameters actually turn out to be thickness dependent as well. So that was giving us the hint as to what was going on. I'll cut to the chase and just show you some slightly mesmerizing videos. So this was a really nice paper just published a few years ago from our PhD student, Becky, where she found for the first time these transitions from various hexagonal states to orthorhombic states. So again, incredibly complicated. We haven't even started to study the superconductivity, the charge density wave states of these materials yet. But this is just in an element. So there's loads of really interesting physics left in elemental systems. That's the thing I want to advertise for this. Okay, last one for me. Hopefully I'm not running over too far. Last one is a different style again. So we've talked about single crystals with the oxides. We've talked about textured materials where it's not perfect single crystal, but kind of almost. And then the last example is actually the very first part of my career, my PhD and subsequent postdocs, where actually we don't care about being perfect crystals. So superconductors, Cooper pairs are big, yeah? So the superconducting wave function often doesn't care about microscopic defects or grain boundaries and things like this. So many of these materials are polycrystalline, really easy to grow, really easy to combine in various multilayers. And that's good for potential applications. It's also good for fundamental science. You don't have to spend ages optimizing the materials. The materials are important, but it's much easier than working with single crystals. So what were we doing? We're trying to combine superconductors with magnetic materials. So here's a superconductor on the left, a ferromagnet on the right. And typically the cartoon argument is, well, Cooper pairs are spin singlets and ferromagnets have their spins all aligned. So they don't really like each other. That's the headline story. But actually on a microscopic level, on the nanoscale, there are a few different tricks we can play. And actually what you will find, there are basically two types: a short range inhomogeneous superconducting state. So for experts, this is like a Folder-Ferrell-Larkinov-Chinnikov state, but also a long range odd frequency S-wave triplet state. And I'll talk briefly about those, and I'll rattle through this fairly quickly because I appreciate coffee is next. So the first one is the kind of first generation of proximity effects. Here's a Cooper pair singlet. You take these two electrons and put it inside a ferromagnet. Inside the ferromagnet, up spins are different from down spins because it's a ferromagnet. So the bands are split. So at the Fermi energy, the Fermi velocities for the up and down spins are different. So the different speeds give you some kind of interference effects. And that's a super fast cartoon argument as to why the superconducting order parameter has this kind of wiggly oscillation. It's a new type of superconductor that we've engineered by combining two materials together. So this was established firstly in Cherniglovka about 20 years ago. They used a weak ferromagnetic alloy, copper nickel. And here they saw this is in a Josephson junction. The critical current is non-monotonic in temperature. And then later in France, they showed a similar thing with another weak ferromagnet, but now they could study this as a function of thickness. So this non-monotonic shape is essentially the same as this oscillating order parameter. You can think of it like that. So we're mapping out that. So that was very nice. We established it later in stronger ferromagnets, cobalt, permalloy, nickel. And this was a bit more challenging because the distances here now are just a few nanometers. So you have to be very careful with your thin film growth. But it allows us now to start to think towards applications. So one of the things I did many years ago was just take a superconducting, take a giant magnetoresistive spin valve, so a spintronic device that you might find in the hard disk drive of your computer, and insert it into a superconducting junction. So now we can switch the Josephson current with a magnetic device. So that was kind of an interesting direction for the future. The second type of superconducting proximity effect is this odd frequency S-wave triplet. So this is very unusual. And the idea is that you basically take this singlet and then you think of a way of mixing the singlet into all possible spin states. And so you need some kind of spin-dependent scattering or non-collinear magnetism. And so let's briefly, super fast, talk through the different options. So the first probably convincing realization of this was from the Delft group, where they used chromium dioxide. So chromium dioxide between two superconductors, and they could see a supercurrent passing between through chromium dioxide over very large distances. This, for me, hundreds of nanometers is a huge distance. Yeah, you remember from the previous slides, we were seeing supercurrents over a few nanometers. This is 2 orders of magnitude larger. So these Cooper pairs pretty much had to be triplet Cooper pairs because chromium dioxide is a half metal. It only carries one type of spin. So there must have been something funny going on at these interfaces to convert the singlets to triplets. The Cambridge group also looked at spiral magnetism. So holmium, elemental holmium, is a Healy magnet. So it has a very interesting conical magnetic structure. That's another way of converting singlets to triplets. You can use synthetic multi-layers, so layers of cobalt and copper. This is, again, what you would find in your computer roughly as a read head in your hard drive. So Norman Burge's group in the US did a huge amount of work using the non-collinear magnetism here, again, to generate an entirely new type of superconductor. And more recently, so in the last few years, people have become increasingly interested in using spin-orbit coupling, again, as we heard in the last talk, to mix the spins up. So instead of this simple spin singlet, you have all the possible combination. And we filter out then the triplet component, which can penetrate into the ferromagnet. So many people in the literature have used a heavy element like platinum or palladium or gold. Of course, I'm interested in using uranium, which is as heavy as it gets. And really the thing is, we've now done some really interesting fundamental physics. And now the question is, can we make devices? So again, actually, Norman Burge's group is really leading the way on making complex devices that look like spintronic devices. This is something you might already see in your computer, but now combining it with superconductivity and thinking, are there new types of junctions, new types of technology that we can really use for low temperature superconducting circuits? Okay, so that was a very fast summary of 3 big topics. I've told you about superconducting semiconductors. I've told you about uranium as a material, a metastable material, and then a little bit on superconducting ferromagnet combinations. But really the important thing is thin films are good at combining together lots of different types of material and physics to do interesting things. Thank you very much.
In one material, the transition from this topological order, electron liquid to superconductor. But
I'm sure there must be. So I think the way I portrayed it as, again, I'm kind of half material scientist, half physicist. So to say, oh, we can just I'll give you some Lego bricks and you can just put them together and then it works. It's not as simple as that. Yeah. So you should think of, come up with a theoretical system, and then it will probably take several years to actually make this work. Because it depends on how, this is a really good example, but actually if you don't get this right, the atoms blur and, they interdiffuse, they mix, and you don't get this idealized interface. And that's a challenge for material scientists. I'm sure there must be examples out there where you can do this, but this particular case has lots of interesting physics, probably not much topological physics, but there are other examples out there, definitely. Yeah. So yeah, we can talk more about that.
Thank you.
Thank you very much.